Okay, right. So you've given us some source material, and our mission, as always, is to really dive deep into it. This time, it's actually kind of unexpected. We're looking at modeling the cooling rate of milk, straight from the farm before it even gets packaged. And the source material specifically mentions using calculus for this. Differentiation, actually. Seems like it's aimed right at college students working through calculus. It's that connection, I think, applying this math to something so, well, agricultural. That's interesting.
Yeah, absolutely. And I think our goal here is really to pull out the main ideas, like how exactly does calculus, specifically differentiation, help model something like milk cooling down? It's all about bridging that gap, isn't it, between the math functions and what's actually happening physically on a farm?
Exactly. And the source really flags the derivative as being key to understanding the rate of cooling. Because, you think about it, the temperature doesn't just drop steadily.
Hmm.
It cools faster at first,
Yep.
right? Then it kind of slows down as it gets closer to the room temperature or whatever's around it.
That's right. And what's really cool, I think, about the derivative here is that it's not just giving you an average change over, say, an hour. It tells you the instantaneous rate. Like how fast is it cooling right now at this very second?
Ah, okay.
And if you're in that calculus class, you know that ties directly to the slope of the tangent line on the graph.
Right, the temperature time graph.
Exactly. That slope is the rate of cooling at that specific moment.
So it's more sophisticated than just watching the thermometer drop over time. You can actually build a mathematical model that describes how that rate is changing. Does the source mention models where the rate depends on the temperature difference?
It hints at that, yeah.
Yeah.
That the rate of cooling might be proportional to how different the milk's temperature is from the surrounding air.
Mm.
And that relationship, that's classic stuff for differential equations.
Okay.
Calculus gives you the tools to set up and solve those, so
Oh.
you can predict the cooling curve much more accurately.
Right. Better predictions. But why is that so important on a farm? I mean, before it's even packaged.
Oh, it's absolutely crucial. It boils down to quality control and safety.
Safety. How so?
Well, milk needs to cool down fast to stop bacteria from growing, right?
Right. Mm-hmm. Makes sense.
So having a good mathematical model, one based on differentiation, it lets farms actually optimize their cooling systems. They can figure out the best way to do it and predict pretty accurately how long it'll take to get the milk down to a safe temperature.
Ah, I see. So it ensures consistency
Yeah,
and helps meet regulations, crop segment.
precisely. It moves it from, maybe guesswork or just rules of thumb to really precise management based on understanding the physics of the cooling process.
So it takes that maybe abstract seeming idea from your calculus lecture, finding a slope at a point,
Right.
and applies it directly to figuring out how quickly this big tank of milk is losing heat. That really does make the math feel concrete, purposeful.
Yeah, definitely. And if we zoom out a bit for you maybe listening and studying calculus right now, this example really shows how these mathematical tools, which might feel theoretical, they actually underpin solutions to really practical, important problems in fields you might not expect. Like agriculture, understanding instantaneous rates of change is just, well, it's powerful because so much relies on how fast things are happening at any given moment. So yeah, to sum up the main point from the source material, differentiation gives us the language to describe and model the rate of change. For milk cooling, that means precise control, better optimization, really important stuff before packaging.
And for you, thinking about derivatives, it stops being just about curves on paper. It becomes this tool that actually helps ensure the food we get is safe and high quality, all based on understanding how fast temperature drops. Okay, so here's something to chew on, maybe after this. Where else could modeling the instantaneous rate of change using calculus be really important? Maybe somewhere unexpected. What other everyday things that seem simple, might actually have dynamics best understood with the derivative? Something to think about.